All right. Hi, everyone. I'm Randy Xu with Luohan Academy. And today we have the privilege and pleasure to have Dr. Neil Thompson on with us to talk about a very important subject. And basically to frame it, right now, obviously in today's zeitgeist, artificial intelligence and, its capabilities and issues are at the forefront of what we're talking about. And chief among those questions, how can it improve our lives and improve various aspects of our economy? And this is something that Dr. Thompson's paper will kind of help to shed some light on, which is an important question of how AI can help accelerate or augment research and development, which is the foundation, obviously, of our social economic progress and prosperity. And in particular, the paper will explore different questions, but among the ones I was very curious about were, how it affects the R&D elasticity of capital, how it affects productivity expectations going forward, and how it interfaces with human capital. So we have the pleasure of having Dr. Thompson with us today. And Dr. Thompson, just for a quick background, is the director of the Future Tech Research Project at MIT, which aims to understand the future development of technologies that are core to our lives today. He's a principal investigator at MIT's Initiative on the Digital Economy. And we have many friends who are also affiliated with IDE. And then, Dr. Thompson, you probably have some of the most extensive set of, academic degrees. You have a degree, undergraduate degrees in physics and international development. You have master's degrees in, if I understand, in economics, statistics, and computer science, as well as a PhD in business. And then you've also conducted research across a wide range of topics that are relevant to all of these, domains, which are on technology, on things like development of Moore's law, on the economics of this, on the patents and business processes of using technology. So it sounds like that you are, very well qualified to talk about the issue at hand today. So with that, without further ado, I hand it off to you to, discuss this paper.
All right. Well, thank you, Randy, for the very generous introduction. I will try and live up to it. So before I get going, I just want to recognize my co-author, Tamai Bejirolu, who's also on it. Tamai. Tamai has been instrumental in this paper, and he will be here fielding stuff in the chat if people have it, and also answering questions as we get there. Okay, so as Renee, as you introduced, the goal of today's talk will be to discuss the economic impact of AI-augmented R&D, right? And this is important because, a lot of the stuff that we're hearing in the press and stuff that, we in our lab are also doing is around the impact of AI on the final goods market, right? Oh, we're going to replace this many jobs, we're going to have these kind of things. And that is clearly like an important impact that we should be thinking about. But we also see AI being used in science. And I'll talk a lot about that today. And this has this promise that, we know for the last several hundred years that progress in science and the innovation and productivity that it produces has been instrumental to the improvement in our quality of life. And we might want to say, well, wait a minute, maybe this mechanism will actually be a really important one for understanding the broader impacts that AI is going to have on society. So that's where we're going to go today. So if I want to start just by saying, if there's a single big question here, it's, will using AI in research and development lead to higher productivity growth? Okay. And the contributions that I think that we're going to make to this question are several. So the first is that we're going to empirically estimate the ideas production function for AI in one important domain. And I think this is important because, you know, a lot of work has been done thinking about how AI might affect ideas and things like that. But it's like being able to combine these sort of macro level, here's what we see, with a very micro level analysis, which you'll see, which when grounded in actually how fast does progress happen when people use AI in a particular domain. Well, how much, you know, how much actual capital has to be put into those things? We're actually going to estimate that in a very fine-grained way, and then we will be able to come back up to the high level and think about the growth impact. And so that's the second impact here, is to use theory, estimate the productivity and economic growth implications that are going to come from this. So, you know, this big piece really is going to say, hey, we think that AI is really important. We'll look at it at a micro level. We'll then expand up to the macro level and say, what does this mean for productivity? But, you know, one of the things that we encountered as we were doing this, as I think everyone who estimates production functions does, is we say, okay, you know, we're going to estimate some measure of capital, right? And we're going to be thinking about computation for most of this stuff. But then you also have to calculate something about labor. And of course, the challenge with labor is, you know, getting your arms around human capital is a tough challenge, right? And so, so we sort of like drank our own Kool-Aid, in fact, and said, okay, well, you know, we've seen how important neural networks can be for science. Let's actually use a neural network to estimate the human capital and see if we can do better that way. And, you know, giving away a bit of the punchline here, we are in fact going to do much better by introducing this new method. And so we'll talk you through as well how we did that. And sort of, you know, in the paper telling you about the importance of AI for research and development, we will show you a particular example that we used in order to do it. Okay, so with all of that said, the place I want to start is to think about the role that AI is having in R&D. And here I want to clarify, I suspect if people called into this seminar, they're probably at least broadly familiar with AI, but I did want to make one distinction that I think is really important. So that is, if we think about artificial intelligence and machine learning writ large, I want to categorize it into three broad areas and emphasize the one that I mean, right? So there's a version of this, which is like artificial general intelligence, machines that think, right? This is this sort of like overwhelming, like we can replace, you know, many of the things that humans do in general with this, right? That, you know, such a development would have incredibly profound implications for things way beyond what we're going to talk about here. So that's very important, but not what we're going to talk about here. There's also what I would call like rebranding, right? So if you think about something like regression or logistic regression or things like that, right? Traditionally, statisticians said, oh, you know, these are our things, and economists said these are our things. And in the modern time, you know, more modern time, you have sort of data science saying these are our things. And I think that because the wage premium on machine learning has so much higher, everyone has now sort of rebranded those techniques as machine learning. Again, very important, very useful. Not really, there has not been any kind of big step change there, so I won't be talking about that either. What I am going to talk about, unsurprisingly, is neural networks. And, you know, this is, you know, neural networks is sort of the old name, right? That goes back a long, long time, but more recently called deep learning. And of course, we're all in the era of ChatGPT, so we're all experiencing this. Okay, so great. You know, we're going to be talking about neural networks. I also want to emphasize just how important these are. And I can emphasize it in particular in the context of large organizations that are doing very detailed compute. So this is a survey that I ran 3 years ago on some of the most advanced US computing users. So these are national labs, big private companies. And so even though the sample is small, it actually represents a fairly substantial fraction of all of the most important computing users, or the most advanced computing users in the United States, excuse me. And I just asked them this very simple question: what is the most important machine learning technique that you're using, right? And overwhelmingly, they said that neural networks was, right? And so I just want to emphasize this for two reasons. So one is that I think that there's been a sense of, wow, like, people like Google are doing this, but how much is it making its way into other areas? And I think the answer is overwhelmingly so, right? Is overwhelmingly the most important. It's also important to say that many of the folks who are these most advanced computing users are in fact ones who are doing science and technology, right? And so you can think of, for example, an oil company, where an oil company, like one of the most important things they do is figure out where to drill. And to do that, they do this very detailed seismic monitoring, seismic evaluation of the ground. And then they try and reconstruct what it looks like. And they say, okay, this based on the reflection of the seismic waves and the spaces, these other things in, we think there's going to be oil here. And so in fact, the oil companies have some of the biggest supercomputers in the world. Okay, so that's, an example, but you also have all kinds of other people doing very advanced science with these machines, and what they're doing is using these neural networks. And so this is starting to give us a hint that neural networks might be quite important for science and technology and advancing it. Okay, so let's now take a step back and say, well, why might this be true, right? We have got lots of techniques. Why should we believe that from some deeper level about what deep learning does, it should be more effective for advancing science and technology? And here I want to emphasize sort of a broad continuum that it exists on, where I want to think about experts versus flexible learning. So let's just imagine we have some broad thing we want to learn, right? Some data generating process. And it's just something out in the world, right? And we say, okay, great. We have a couple of options. So we can model it with a very inflexible approach or a very flexible approach. So what do I mean by that? Well, we think about a low flexibility approach. We can think of this as like you might call it a domain expertise approach. And most of the stuff that we do as economists falls into this category. So you take a small number of features and you use judgment to pick, right? So you have this like, okay, I'm only going to write this regression and it's going to have 5 variables in it. And I'm going to choose which variables, and how am I going to choose that? Because I know something about the world. And so what I'm sort of doing is saying, like, I know this thing about the world, and I'm going to estimate exactly how it's interacting with it. Okay, so the good news about that is that, like, if you have a small number of features, it's going to be very computationally effective, right? Very efficient, great. But you also know that it's going to miss important features, right? And I think this is sort of more clear to economists than it is to maybe computer scientists. But it's, it's entirely common to run a regression and be like, oh, I explain 20% of R squared, right? And that's sort of like 10 to 15% will come up later as we think about human capital, right? Often if you model human capital using something like the number of citations that people get or something like that, you're going to get an R squared of like 0.15, 0.2, something like that. Okay, and so what that's telling us, right, is that the good news is it's like we know enough to put some stuff in that's very explanatory, right? And we usually get, highly statistically significant results. The bad news is there's a ton of variation we're not explaining. And it sort of raises this question, okay, what are we missing? At the other end of the extreme, you can think of deep learning. And this includes just enormous numbers of features. Okay, and I think one thing to think about enormous numbers of parameters, and I think the important thing to think about here is that, like, it's as if you are writing out these regressions and you're including higher order terms and interaction terms between the higher order terms, right? And so when I say features here, I don't just mean like that bottom layer of the neural network. I mean that implicitly in the neural network, you're doing all kinds of transformations of your base variables, right? And that is effectively, in the way we think about in a regression, like running this huge kitchen sink regression with all kinds of things in it. And that's going to allow us to account for way more of the R squared, right? The variance that we might want to explain, but it's going to take a ton of compute. And of course, this is going to raise some questions about how we can do some interpretation. All right, so what I want to highlight here, right, then is on this domain expertise side, right, a lot of it is guided by, we know something about the world, and, we might have some theories about other things that could affect the world, and we include a small number of things there. On the right-hand side, we're going to sort of throw the kitchen sink at it and try and figure out what's going on. And the good news about throwing the kitchen sink at it is that we're, in general, going to explain much more about what's going on, and we just have to figure out some way to learn from it. And of course, if we can learn from it, that might be quite powerful. And, you know, I think a really nice example of why we actually can learn it, it comes from some work that is done by some of the folks in my lab. So one of my postdocs, Sung Choi, did some work on the game of Go, right? That we know that the systems, that artificial intelligence systems that play Go can now beat humans decisively, right? They're much, much better than humans. But what's interesting is that after AlphaGo comes and wins this contest, humans start also getting better. Still not anywhere near as good as the system, but the actual quality of what the humans are doing goes up, right? And that's because even if we can't understand exactly what AlphaGo is doing under the hood, because there are just too many parameters to interpret it all, we can nevertheless look at it and say, oh, it's making systematically different choices on the first move than humans were making before. We can now explore that space ourselves and try and figure out what's going on. And so we have this interesting fact that, like, this more flexible approach allows us to discover things about the world that we didn't know before. Okay, so far I've said, okay, here's why we might believe that this flexible approach gives us a method to learn more about what's going on in science. And for example, by making very good predictions and then learning from those predictions, or just, the predictions themselves are sometimes very valuable for science. And I'll talk about an example of that in a little bit.
Oh, can I ask you one quick question?
Sure.
Yeah, I'm actually a bit embarrassed to ask this question. Yeah, I heard about the deep learning a lot, but can you explain, like, very quickly, what is the big, the difference? What's like a feature of the deep learning different from the regression? Just like I'm kind of ignorant about this field.
No problem. I think it's a very good question. Yeah. So I would say there are a couple of different ways to answer this question, but let me give you one which I find the most helpful for thinking about it, and we can talk about other details if you want. So, like, when we typically write out a linear regression, right, we're often making this very distinct choice where we're like, everything here is going to be linear, right? And we often go through sort of Herculean, theory things to, like, well, if this is logs, then we can turn it into some linear thing. So the first thing that is true about deep learning is that it's nonlinear. You have these big nonlinearities inside it, and that's a little bit like if you're adding a whole bunch of higher order terms, right? So if you add x1, but you add x1 squared, x1 to the third, x1 to the fourth, right? You're allowing these discontinuities to be there. And so in deep learning, you have a very specific one that's called a ReLU, which is like, if you're below something, you get nothing. Below some threshold, you get no response from a neuron, and above it, you get a response that's typically linear in the inputs. So that's like, and so that is, from the context of a regression, that's basically like including a whole bunch of higher order terms. But if you've ever seen a neural network, you often see that there's sort of a bottom layer that has the inputs to the network. So these are the traditional variables we would think about putting in a regression. And then we have these, like, a layer above it. And what you've done is you've basically taken a linear combination of the things below it, and then you take them and then you pass them through this nonlinearity, and you get this other effect, and so on and so forth. So that's like if you ran a linear regression and you put in a whole bunch of terms where you'd say, like, okay, I've got b1 times x1, and now I'm going to have b2 times x2, but then b3 is going to be, x1 plus x2, and b4 is going to be, b x1 squared plus x2, and so on. So you just have this, like, enormous, right? And I mean, think about having, like, billions of terms in your regression. Okay, and that's effectively what you're running. Now, you wouldn't, in practice, you could run a neural network this way. You could do sort of the least squares kind of analysis that we do. The problem is that it's so computationally expensive when you have that many variables that people don't. They use this gradient descent approach within it. But effectively, what you're doing is estimating just this incredibly complicated regression, right? That is where you've allowed yourself lots of nonlinearities and lots of, like, x1 plus x2 divided by 7, to the power of 4 plus x12, blah, 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 right? You're allowing yourself to do that. Is that helpful? Did I answer your question, or can I answer it in a different way?
So it's like basically non-parametric estimation. Is it correct? Is it different?
Yeah, so right. So a really important part of the theory around neural networks is that they're universal function approximators, meaning that like at whatever sort of function you have, if you have a big enough neural network, you can map it in a very non-parametric way. That's right.
Okay, yeah, I got it. Yeah, thank you. Thank you for the answer.
Yeah. Great.
Can I ask a question?
Please.
This is Bengt. Is it fair to say that this can have really big payoffs in sort of more general settings regarding the problems of sort of gradient traps? That is, you go for local optima when you optimize, and this. I think you have the AlphaGo. How was it that the humans suddenly started to learn more? They realized there's an entirely different part of the space where they can operate, and you can imagine that these are kind of traps that we end up in. We don't experiment. All sorts of shocks. We see actually now what's happened in people staying home, for instance. Now they suddenly sort of woke up to it and realized that may be a good idea. So do you have any comment or sort of, this is a little bit expanding on your theme, but.
Yeah. This I think this is a great question, and so I think clearly in the case of AlphaGo, I think that's exactly what happened, right? It was particularly in some of those cases where you can do what's called reinforcement learning, right? Where you're sort of learning. So like AlphaGo, sort of one of the things they did, particularly when they did to the next level to go to AlphaZero, what they did is they just had the system play itself many times with all kinds of different strategies. And so it was exploring a much bigger space, and exactly the way you're talking about, where it can find a peak that humans have never explored. But there's been an outstanding question in deep learning theory for a long time, which was like, why doesn't deep learning just get stuck in these very local optima in a way that you might really worry about, right? Because traditionally we think of, as you add more and more parameters to a regression, right, you more and more end up fitting noise, and you end up in some weird, like very corner case where you're saying like this doesn't seem like it's actually the best solution. And the answer seems to be some combination of two things. So one is you have this great over parameterization in deep learning. So you have many, many more parameters than you have data, right? And traditionally in economics, we're sort of allergic to that idea, but it turns out that what you end up with what's called a double descent phenomenon. So if you take, if you imagine you take your regression and you have, say, 100 data points, and if you start adding variables to it, you start explaining it better and better, and then at some point you, like even on your training set, you would continue to improve, but on a test set you get bad because at that point you're fitting noise, right? And so that's typically what economists have thought about as the place where you have to stop and turn around. And but it turns out that if you sort of continue on and you have way more variables than you actually have data points, then you actually end up in the second regime where your error falls again. So the first thing that happens here is that you have this way over parameterization. This produces a super interesting result that is very directly to your question, Ben, which is you ask the question, well, like what happens if a neural network is in what you might call like a local minima, right, and not in the global minima? Well, the thing is, there's so many dimensions that a neural network has that in some subset of those dimensions you might be in a local minima, but in some other ones you can just walk straight, right? So there's no gradient at all. You can just sort of walk along it, and that means that you could sort of, every point is not actually like a total minima. It's just like a saddle point of something, or like a valley. And so you can keep walking along the valley until you find a deeper hole, right? And so that's why people think that as long as you're willing to run your neural network and you have enough data, you can in fact continue to progress and find these more global minima, like the ones that you were referring to.
Okay, I'm going to take moderator prerogative and suggest that we maybe move on, and if there's more questions on this, we can cover it later.
Sounds good. Okay, all right. So this is sort of telling us, right? And after some great questions here, we can sort of see why deep learning might help us to do science. But it's going to come at a cost, and it's going to be a very interesting cost, which is using a lot more computation. And so a nice graph of this came from Andrew Ng, and this is our adaptation of this. But it says, okay, well, if we think about how well a model is going to do, so you can think of something like accuracy or how good the prediction is or something like that, and you think about the amount of compute that is going to be used here, and compute, obviously, if you use more data, you're using more compute. So those two things are going to go together here. Well, if you think about a regression, because you don't have very many variables, when you first only have a little bit of data and a little bit of compute, you actually can use it very well, right? The few data points that you have contribute a lot to those estimations. And so initially your model does quite well. And then at some point you hit that point I was mentioning where it's like, okay, the variables you put in have explained everything they can explain. And then there's things you just didn't think of. And so you end up plateauing. Right. And so, I could give you 1,000 times more compute. If you run the same regression, it doesn't help you very much. Right. And, similarly, if I give you even 1,000 times more data, like you probably get a little more precise in terms of your standard errors, but not like only in sort of a central limit theorem kind of way, not in a way of like, oh, I'm explaining a whole bunch more stuff. Conversely, with something like deep learning, you have so many parameters that initially you are training incredibly slowly. Okay, so you just, you use your first 100 data points. If you imagine you have 1 billion parameters, right? You've made almost no movement in them. And so at the beginning, you haven't learned very much. But the really interesting thing is if you keep adding data and keep adding data and keep adding data, eventually you outperform these typical models. Right. And I think a big story of why deep learning has taken off the way it did is that we had these crossing points where suddenly we had enough computation and data to be in this kind of regime where it outperformed, whereas historically we were in regimes down here where it wasn't worth doing and we were better off using a regression. Okay, so the reason I bring this up, right, is we're going to talk about the role of using more and more compute. And what you can see here is there's a different return to using compute with deep learning than there is with other things like linear regressions. Okay, so we're starting to see the mechanism that we're going to talk about in this paper, which is that deep learning is more capital intensive, in particular more computational capital intensive than other places. Okay, so that's where we're going to go. I do want to point out that this is it's not new. So I mentioned it was clear that deep learning here, it was computationally expensive and was a problem. This actually has been known since the very first paper written on neural networks by Frank Rosenblatt back in '58. And he said in that as the number of the connections in the network increases, so that's the number of parameters, right? The burden on a conventional digital computer soon becomes excessive. So much so that in fact, in some other work that Tamai has done, you can actually see deep learning and machine learning in general being constrained by the kind of computers that we can have. So here's some work that he has done with some of his co-authors. And what you can see here is the amount of compute that's being used, right? And notice that we're on this scale where we have a factor of 10,000 between these points, right? So these are enormous increases in compute. Right. And then we have these models, which are sort of the most important models by several criteria. I think that the term they use is noteworthy models of machine learning over time. And you can see that up until about 2009, you have this much shallower line. And in fact, if you look at the parameterization of this line, it's pretty close to Moore's law, meaning that as computers got more powerful, people said, okay, well, I used to use, 2 computers or 10 computers for this. Now I'm going to use 10 computers for this. And those computers are much more powerful, so I can do more, but I'm not spending, 2 orders of magnitude more money on it, for example. And then after 2009, 2010, we see this break. And we see all of these models going rapidly up, right? And that represents a huge increase in the amount of spending that people are doing on these things, because it represents this moment where we passed into this region, I would argue, right? Where suddenly we say, oh, wow, we can get better results. And now as soon as people discover that, they're like, let me push out the compute and push out the compute and push out the compute to go up this curve. Okay. So again, we have this nice evidence of this huge escalation in computational capital being used. To give you some sense of the magnitude of this, so Facebook or Meta, right, when they introduced their AI research supercluster back in 2012, and some journalists did some digging and tried to figure out, okay, well, actually, what's the cost of that? And what they said is, we estimate that at list price, this machine would cost around 400 million, with 303 million of that just being for the GPUs that are being used. Okay, so we're talking about very big science in the sense of 300 million for one company's machines to do these kind of things. This is big money. But this is by no means the only place where we see these kind of breakthroughs happening. We can see them much more broadly. And so a really interesting one back in 2021, that came out of Google was reinforcement learning for chip floor planning. So planning out the alignment of a chip is an incredibly, complicated, difficult thing. We have for decades built tools around this. The reinforcement learning technique did basically as well as humans, and it did in much less time. So that was really interesting. One that I will talk about more in a second, but is, I think, a really just crucial one here is AlphaFold, protein folding. I'll come back to that in a sec. Controlling fusion plasma in a tokamak. So, like for decades and decades, we've talked about getting fusion, right? Like this may help us control the reactions so that we can get them. And then I think, a much more sort of mundane, but I think actually probably very far-reaching one is stuff like GitHub Copilot that helps people code. And so again, you can imagine that, if one of the tasks that you're doing as a scientist is to write a bunch of code, which I think is the world we all live in, right? Having some system like this that can help you write your code much more quickly is going to make you a lot more productive. And so that's another example of using capital to make yourself more productive. Okay, so to just end on the science side of this, I just wanted to give one more very concrete example, and which is in protein folding. And protein folding, I think, is a particularly interesting example of this because it's one that people have been trying for a long, long time to get better systems to do and really struggled with, right? So this was an area where humans, up until maybe 10 or so years ago, humans were still like looking at proteins and making predictions because they somehow were able to figure out what was going on there better than the machines were able to do. And what's remarkable is AlphaFold from DeepMind has totally blown the existing systems out of the water, right? And now does an incredibly good job. People believe it's going to be an incredibly important tool for synthetic biology and biology in general. What I want to highlight here is just how important computation was to that progress, because it turns out that DeepMind was not the only people we're not the only people thinking of using deep learning for this problem. Others labs did as well. And you can actually plot those on a graph, and this is what you see. Okay, so on the x-axis here, we have the amount of compute being used. And again, notice we're on a logarithmic scale here. So each of these is a jump and tenfold in the amount of computation. And this is the prediction accuracy on the big sort of contest that is done. So this is a measure of like how well your predicted folding matches with the real folding. And so here are a bunch of the other labs that were doing work using deep learning to try and solve this problem. And here's AlphaFold version 1, and here's AlphaFold version 2. And what I want you to notice here is that the AlphaFold 2 is 1,000 times more compute than these other labs, right? It's very predictable. You can see it's quite a good fit here, but they just were able to harness way, way more computation in order to do it. Okay, so broadly, what I want you to take from this section is just AI can have a big impact in science, but it is the nature of deep learning and how it does it that it's going to be using a lot more computation. And in fact, that is often summarized in what are sometimes called scaling laws, emphasizing this. Okay, so deep learning's flexibility allows us to learn. Deep learning success has required enormous increases in computational capital, and deep learning is already generating important discoveries. So these are all reasons why we might think this is really important. let's now take this to a growth setting to think about what this might mean. Okay, so for our growth model, we're going to use a semi-endogenous growth model following Jones. And the idea is that we're going to have some final goods production in the economy, right? Pretty typical. We're going to have capital with some decreasing marginal returns. We're going to have labor with some decreasing marginal returns. Here, we're just going to assume that we're in a constant returns scale. And then we're going to say, okay, we have some idea production at the frontier. You know, often when we write this down, we write this with theta is equal to 1, but of course, it doesn't have to be. And in fact, you know, some of the estimates in the literature are putting, you know, put this between say 0.5 and 0.1, between 0.5 and 1, and we're going to use 0.5 conservatively in what we do our estimation. But we're going to think more specifically about, well, where does this come from? Where does this, and what is sometimes called the ideas production function? And we're going to say that when we get some increase in that, that's going to come as well from some factor of the capital that's being used here and the labor that's being used here. And so, you know, what we're going to have is in the economy, we're going to have this exogenous division of the labor. So some of the labor is going to be in the final goods production and some is going to be in the ideas production sector. And similarly for capital, some fraction is going to be here and some fraction is going to be there. Okay. Then we're going to say, all right, well, you know, what are the dynamics in this model? And we're going to just have labor grow exogenously, right? Okay. And then we're going to have capital, say, basically increasing as with the with the overall economy, right? So there's going to be some savings rate, and as the economy gets bigger, we're going to put more into capital. But there's also going to be some depreciation rate on the existing capital we have. And what we're going to look for is there a balanced growth path that actually fits this? Now, very important for this, you know, we're not the first people to think about this idea of AI in this world, right? There are things, for example, by Coburn and all, where they've said, okay, actually, we should think of AI as an invention of a method of invention, right? And this is this idea. And so actually what we're going to be doing is testing. Okay. Now, I've already sort of previewed for you where we're going to go here, right? Because we're going to think about the capital intensity of deep learning in science. And I just want you to think about what's going to happen here, right? So if we move from a previous era of machine learning to the current era, right, we're going to say that, okay, if we can harness capital better, that's like beta going up. Okay, and so that's going to generate a bunch more knowledge in the economy. That's going to lead to the economy getting bigger. And because of this, we're going to accumulate more capital. We're then going to invest that capital in both the final goods, but also in the idea production function, which is going to make us more productive. And so we have this possibility of this reinforcing cycle that leads us to a higher growth path of more rapid growth. And that's what we're going to show. Okay, so let me actually talk that through sort of visually to make sure that that's clear. So this is just taking that graph that we looked at before, using some of the parameterizations that are in the literature for those parameters and saying, okay, what does the capital share in R&D imply about the steady state growth rate? And so what you can see here is on the, and here we have the productivity growth rate, to be more specific about that. And you can see that at sort of like 1.3, something like that, that's the average US productivity growth from 1950 to 2020. We have also the peak of the 10-year growth is a little over 2%. And this dark line here represents that parameterization, right? So if your capital share in R&D is down here, you'd expect about 1% growth. If it's up here, you'd expect 2-3% growth, et cetera. Okay, so that's that feedback mechanism. And this is just the sort of resulting equilibrium that you get from it. Okay, so the first thing you might ask is, well, traditional science, right? We do lots of that. Where does that sit? And so it turns out that the NSF Higher Education Research and Development Survey allows us to look at what academics are looking at in terms of these different areas. And we can see that in areas like life sciences and health sciences, actually only about 4% of the research expenditures are going to capital. And this is all forms of capital, not just computational capital. So these are incredibly labor-intensive areas of it. Okay. Computer science, not surprisingly, a little higher, more like 12%. Okay. And at the very high end, you have engineering, like so physics here, material science, but in this sort of 15 to 20% level. Okay, so at least for me, I guess I'd never seen these numbers before. I was sort of interested to see them, but it sort of tells you roughly the level you have. And so if we go back to this chart, right, it's sort of showing you that we are in about this era, this region here, and that sort of makes sense with where we are. Okay. All right, so our approach then is going to be to estimate the ideas production function, right? Use it with AI. So we're gonna, for capital, we're gonna focus on the computational capital in these models. And we're gonna augment and update the database that my lab put together back in 2020 of the compute being used in deep learning, particularly, and we're particularly gonna focus on computer vision as that area. And then in terms of the labor side of things, we're going to estimate the human capital using deep learning archive papers using a neural network. Okay, so let me get into the heart of this, right? So as I say, we're going to use computer vision. So this is going to include image recognition, which is probably the one that people know more, but also object detection. Image recognition is this idea of, I show the computer a picture of a cat, and it has to tell me it's a cat. If I show it a picture of some baseball players, it tells me it's a baseball diamond or the following. And we picked this area because it's the one that has the most data in terms of time. So the real paper that kicked off the deep learning sort of spread throughout all of machine learning was this 2012 paper, AlexNet, which won this competition that is done on ImageNet and showed how important it could be for computer vision. Okay, so let's think about the capital that's used in this. And this is that data set that I was just telling you about that our lab had created. And so what we're looking at here is on the x-axis, we have the number of operations that are being done, and we've normalized it to that paper I was just mentioning to you, that AlexNet paper. So that's what 1x is. So 10x is 10 times more compute, 100 times more compute, 1,000 times, etc. And on the y-axis here, we have the error. So if I give you that picture, what's the percentage chance that you're going to if I pick a random picture from that one, what's the chance that you're going to make a mistake on it? And I want you to notice that both of these axes are logarithmic. So what we're looking at here is a power law, right? And so what you can see is this incredibly good fit, right? That in fact, we can explain 70% of the R squared of performance in this task just by the amount of compute that's being used in it. Okay, so this definitely says compute's really important. It's really important over this whole range. We have these very predictable returns to it. Okay, what about on the labor side? And so here, as I say, we're gonna do a different empirical approach. So we're gonna, previous work often focuses on citations or H-index indices. We're also gonna use some of that data, but our approach is gonna use a neural network based on paper features to figure it out. And so just to be clear, so that people know we're not testing and training on the same thing here. So we're gonna partition our data. So we've got a bunch of these models where we know how much computation is gonna be used. We're gonna hold that back. And then we're going to take the rest of a whole bunch of archive papers, tens of thousands of them, and we're going to say, okay, can we predict based on a bunch of the features about the authors and what actually is going to happen in terms of the citation pattern, the journal, we'll call the journal it's going to get in, etc. And we'll do that on a training set, and then we'll have a test set to look at. Okay, so let me make that more concrete, right? So if you take this set of archive papers, right, we have a whole bunch of information about the authors, and we have about the publication ID, right? And so what we're going to do here is we're going to say, okay, we can take the author IDs from there. We can go to Scopus. We can also look at some other institutional metrics and grants that these folks have. And that's going to allow us to calculate for each of them an H-index, a publication count, prior citations, etc. So we have basically a panel where at every point in time, we have a whole bunch of information about each of the authors that are on each of these papers. We can also go to Scopus and we can say, okay, we can find out the publication date, the number of authors, the number of authors of different institution types. Now, we can also then use we can also look at how good the actual journal that was published, but we're not going to use that, nor are we going to use the citations that comes from Scopus. We're going to carry that along here to the other side of the model. That's going to be our ground truth that we're going to check against. So we are going to have this vector, which has information about the authors and his information about the timing of the paper. And we're going to say, okay, we're going to put that through a neural network, which I'll show you on the next slide. And then we're going to make a prediction. We're going to make a prediction about citations, and we're going to make a prediction about journals. And then we're going to check that against the ground truth. And there's going to be some loss function, right? And this is a typical neural network setup, and we're just going to minimize that loss to get to the best prediction that we can actually get to. And as I say, once we have a model, right, that is good on the training set, we will then take it to a test set, which is separate, and ask how good our model actually is. So before I get there, though, let me show you this neural network as we actually do it. Now, for those who are new to this, I don't expect you to be able to parse this too much. It's not super important. The key thing is we have that input layer. So we have, again, those properties of all of those authors and stuff in this long vector. In fact, it's a vector that's 179 long. And then we're going to put it through a big neural network that is ultimately going to have as its output one single neuron, right? What we're going to call the human capital unit, right? So for those who are familiar with encoder decoders, that's what this is. Intuitively, basically what you're doing is you're forcing it to do a dimensionality reduction to one dimension, and then you're going to expand that out. And so we take that single prediction, then we interact it with the publication date, and then we allow basically a linear regression on top of it to try and predict the citations in T+2, and the scientific journal rank. Okay, so just to make sure this is clear, what we've done here is take the human capital unit, right? We've narrowed this 179 vector, we compressed it into a single scalar for each author. And then we say, okay, based on that, we should be able to predict the number of citations that people get, their paper is going to get, the number of, and the rank of the scientific journal. And our success is going to be how well we do that. Okay. And so, but the key is going to be, we have this human capital unit, which later we can put right in our regressions for the human capital that was on a particular research paper. Okay, so I don't have too much time left, so I just want to emphasize how good this method is compared to previous methods. Okay, and so what we have here on the x-axis here are the things we're trying to predict, right? So maybe we're trying to predict the log of citations received after 1 year by the paper, after 2 years, 3 years, and 5 years, the index, the rank of the journal, and this blue line is our estimate, right, in terms of the correlation coefficient, and all of these others are doing a prediction based on the maximum H-index of the authors, the sum of the H-index, the mean number of publications they have, yada, 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 whatever you want to use, all of these typical measures. And you can see that they typically get between sort of 0.1 and 0.2 in terms of correlation, and we're very routinely getting 0.7 on these ones. Okay, so it is just enormously better at predicting human capital. Now you might say, well, wait a minute, you've given yourself a whole neural network, you're allowing only unidimensional improvements in these others. You can also look at this if you use a lasso regression for these other variables. So this is, again, these are the predictions we're going to try to make. And what we can see is the precision of our estimate is vastly higher than a lasso using these inputs. Okay, so we do all this. We're going to get then our regression that is going to estimate for image classification and object detection, the elasticity to capital and the elasticity to human capital of progress in these different areas. And you can see we're going to have a couple of different models here, depending on whether we want to include a time trend or not. Now, in this context, it's a little hard to see. So let me put it back in the context of the other areas of science. What is this telling us about, in fact, is deep learning more capital intensive than other areas of science? And the answer is dramatically so. So this is, the left-hand side of this is what I just showed you before, right? This is all of those other areas of science, and this is the capital cost share there. And you can see that if we either take image classification on its own, it's at about 30%, object detection is maybe at more like 43, 44%, or if we pool them into computer vision as a whole, we get something like 35, 36%. So this is dramatically more capital being used per scientist. And, that we should expect, all other things equal, that's going to make these scientists more productive and is going to lead us, based on our growth model, into this world of much more productivity improvement as time goes on. And in fact, what we can do is take these capital shares that we just mentioned here and plot them back on this graph that we saw before. Okay, and what you can see is, again, so these are the different models. A1 and A2 are for image classification, B1 and B2 for object detection, and computer vision. These are the pooled models. And what you can see here is, we're, by moving into this range of much higher capital cost shares, we end up with productivity growth rates that are more in the 2 to 3% range, compared to our current region in this sort of like 0.7 to 1.3 range, roughly. And so you can see that we're implicitly saying something like a doubling in the productivity growth rate that we see. Okay, so let me just, I want to just make sure that it's clear what point this is making, right? So first thing it's saying is deep learning is dramatically more computationally capital intensive than these other areas of science. That has the potential to push us to this right-hand side of this graph, where if all scientists, researchers and scientists in the field adopted this, right, assuming we could roll it out in this way, and there's good evidence that the techniques we're using in deep learning do generalize quite well. In fact, people have written papers about how well ImageNet those techniques in ImageNet generalize to other areas of deep learning use. That seems very promising. But there still is this important assumption of like, if we roll this out through all of science and technology, here's what it would do, right? But you can also say sort of differentially, what this would mean is if only some areas of science adopted it, you would still expect them to move to this higher capital intensity and therefore higher productivity improvement, and that leading to more ideas production and then ultimately to more economic growth.
Hello?
Okay, so I'm almost out of time. Let me just summarize. Sorry, go ahead.
Hi, Neil. Thank you very much. This is Long. And may I ask a question?
Please.
We've known this, the so-called Thorough paradox. So basically, he commented that we see computer everywhere, but we do not see productivity in statistics. So, and it's been debatable for quite a long time up to now. And so we've never quite figured out, is this a productivity issue or is it a measurement issue? So what do we take from your study here? What do we expect somehow acceleration of the growth rate, AI powered acceleration, or we are still going to see the paradox of we do not observe the productivity? What do you see here?
Yeah, so I would say that so I think my view, and I think the reason people, the reason it is a paradox is that I, like everyone else, see IT over the past 40 or 50 years transforming all of society, right? And so when we make these estimates that say that it has had substantial but not that big a productivity influence, right? It makes me think that actually what's driving that is measurement error, right? And there's sort of a long literature of people saying, well, like, let's account for IT differently, and when they do it, typically they get a bigger contribution. But I still think where we are in terms of measurement is not at the actual impact that these things are having. And in fact, if folks are interested, I'm happy to talk about our lab is doing lots of stuff to try and measure some of these things better. But in practice, to get to your specific question, I think what we would expect from this paper is that there should be an increase, a substantial increase in the amount of growth that we would get as people deploy deep learning in all of these other areas. That's a very valuable thing, and that we might, if we then after the fact went back and tried to account for it, right, we would undervalue it in the same way that people have evaluated IT in the past, in so much as we're only able to measure it badly. right? And so, you know, if you, for example, someone said, well, we're going to look at areas of science and we're going to say 0, 1, whether or not they use AI or deep learning in it, right? That's going to hide all of this variation in the amount of compute that's being used. And so that's going to introduce a lot of measurement error, and we're going to underestimate. And so I think, you know, the more precisely we can get to the things in the technology that matter, the more we'll actually be able to see the improvements that would come, not have the solo paradox reinstantiated again.
So I have a final question. So do you differentiate between the, you know, the general capacity of AI versus the applications? Now we're seeing the ChatGPT is like the general purpose technology now, and people can see that as a lot of the applications will come up, a lot of innovations. So in terms of the, I think one of the main predictions I'm getting from your study is that there's going to be a lot more investment in capital in this kind of stuff. But do you differentiate here between the general purpose technologies like the Google, Microsoft spending a lot more, but then make it commoditized, make it available to everyone else like the internet, or it's the application itself? A lot of the application in different scenarios, industries also showing this pattern of the much more intense capital expenditure here. What do you think?
Yeah, so I think the, you know, the sort of general purposeness of these deep learning techniques, I think you can sort of bring in two different levels, right? So there's one level which is, you know, that universal function approximator part of it, right? You can understand why it's been so successful in so many different areas of I mean, both science and, you know, just generally the economy, because it is flexible enough to match any of these things. And so that gives it this kind of power. And then of course there's sort of like at the economic level where we say it's useful in lots of places. I think where that manifests in this paper would be an assumption about like, how broadly could you use it, right? So if you think that, for example, there's some areas of research and development that deep learning couldn't touch, it just is the wrong fit, wrong tool for there, right? Then our results are not going to impact that area. They'll impact other areas. Whereas if you think that it's a more general one, then you think that these results should actually generalize across research and development, and we should expect a lot more improvement in all areas. What I would say is that I think that in practice, we've seen lots of improvement and lots of investment in these things. And so I think there's good reason to believe that it will at least be quite general. But exactly, you know, to the full extent or not, I'm not sure.
And Neil, just a quick check. Are you able to go over a bit to do a proper wrap up? Or
Let me
have a hard stop at some point?
Yeah, let me just check here. Yeah, so I will have to go. I have a pretty hard stop, unfortunately.
Okay.
So I can go about one or 2 minutes over. But so let me just, I mean, I think I have said everything that I was going to say on my summary slide. So let me just stop sharing and we can take a couple of last questions. Okay, so let me make one then sort of parting thought. Oh, I'm sorry, we have a question?
Yes, this is Regina from Luohan Academy. So I have a very simple question. When you're talking about neural network effect, is that something different from the network effect we usually talk about in economics?
Yeah, so yes. So even though so both neural networks and the general networks that we think of in economics, right, we think of like as sort of being this connection between nodes. And but in this context, the neural network is really sort of a data processing thing, right, rather than sort of the social interactions that we think about in terms of the network effect. And so yeah, pretty distinct in terms of sort of what they mean and how they're used. Okay, so let me just, end on one parting thought, because, I think one of the things that's really interesting about our results is that it speaks to, so there's, people in my lab and others have written about this concern about computational use in deep learning, right? That there's been such an escalation that there are real world impacts in terms of, being incredibly expensive, but also producing a lot of carbon dioxide emissions and stuff from running these computers as much. And what I think our paper is saying is, there's like, that is in part in response to the fact that the returns to capital have gotten greater. And that actually is telling us that there's this very positive impact that it can have, because it feeds back into the economy and then produces more innovation, more productivity, and ultimately more economic growth. And maybe that's a good moment to end on.
Okay, that is a very optimistic note to end on. So Dr. Thompson, thank you so much. We really appreciate your comprehensive presentation, sharing your insights on this crucial topic. I hope you don't mind if we follow up with you on, as you do various work in this area.
Happy to.